So viruses need your cell's machinery to reproduce themselves. A virus starts this process by using the keys on its surface to gain entry. Like a Trojan horse, it enters the cell. The virus releases its own DNA into the unsuspecting cell and hijacks the protein-making machinery. Now, this vital cell function becomes an assembly line for new virus particles. No longer in service to your body, the cell now serves the virus, manufacturing thousands of new virus particles, which are released to enslave more cells, thousands and thousands more. The immune system's first defense is our skin, the largest organ of our body. The skin covers a total area of about 2 square meters, the size of a typical basketball backboard. When microbes attack, they're routinely deflected by the skin. Inside our bodies, mucous membranes are slimy, warm surfaces that make up about 400 square meters, roughly the size of an entire basketball court. They're under constant attack from microbes in the air we breathe and the food we eat. They line our nose, throat, intestines, and reproductive tracts. That's a large area to defend. Your mucous membranes are going to need help. Fortunately, certain cells in your body have evolved to fend off microscopic attackers. Early responders, like this macrophage, identify invaders and attack. They also give off chemical signals, called cytokines, to call up reinforcements like neutrophils and natural killer cells. Macrophages, neutrophils, and natural killer cells, collectively referred to as innate immunity, are nonspecific, often sacrificing healthy tissue to contain an infection. But if the invader slips through, you're going to need a more targeted defense. The adaptive immune system provides a more targeted defense. Dendritic cells are like intelligence specialists. They collect pieces of the invader at the site of the battle. Then they travel to the nearest lymph node, triggering a cascade of events. Inside the lymph node, the dendritic cell presents pieces of the invader to T cells, the immune system's communication specialist. In turn, T cells activate B cells, training them to form antibodies, the molecular weapons that target the invader specifically. The immune system now mounts its ultimate defense. B cells release millions of antibodies, each antibody's shape tailored to identify and neutralize the enemy. The immune system deploys these tailored weapons until the infection is wiped out, ready to respond even faster the next time. In 1925, 20 dog sled teams ran an emergency relay across Alaska to save the town of Nome. The threat? A raging diphtheria epidemic. It would be 2 more years before a vaccine against diphtheria would become available. But diphtheria antitoxin was the next best thing. In a 675-mile race against time, the rescue mission saved the town by delivering antitoxin with its key ingredient: antibodies. A vital weapon of the immune system, antibodies are designed to fit and attach to specific invading molecules. Without them, diphtheria toxin attacks nerve cells, heart cells, and kidney cells. Once attacked by these deadly molecules, the cell stops functioning and is doomed to die. By attaching to the cell's receptors, the toxin burns through cell after cell, attacking nerves that control breathing, heart rate, or kidney function. When antibodies arrive, everything changes. Instead of attaching to the cell's receptors, the toxin now binds with surrounding antibodies, blocking it from attaching to cells. But diphtheria antitoxin provides only temporary protection because its antibodies will run out. This is called passive immunity. When the immune system makes its own antibodies, it's called active immunity, which is what a vaccine creates. Through a series of steps over many days, the immune system makes the needed antibodies, now forever ready to quickly deploy its weapons and prevent a future attack, eliminating any need for heroic dogs, brave mushers, or frozen antitoxin. In nature, changes take place almost imperceptibly. But if we condense time, even the most subtle changes become an event for anyone to see. Time-lapse shows us in seconds what happens over many hours, days, or even months. This is how Maurice Hilleman discovered the secret of influenza. By lining up strains of the virus in chronological order, Hilleman was able to see these viruses change over time, like a series of photographs. Most viruses don't change, so it's easy for our immune systems to recognize them from one year to the next. Influenza virus is different. The keys on its surface change with each generation. Antibodies to this year's virus may not attach to the surface of next year's virus. Inside your lungs, influenza virus will quickly invade healthy cells. While your immune system adapts to the new keys on its surface, the virus continues to reproduce and mutate. This is the secret of influenza's survival. With each duplication, the virus changes, altering its surface keys slightly. In this way, it avoids detection and always stays one step ahead of the immune system. Sped up, you can see the viral keys mutate. These changes are hard for the immune system to recognize. Such gradual mutations are called antigenic drift and are why we see new outbreaks of influenza every year. Another way influenza viruses change is by antigenic shift, which is far more deadly. Influenza viruses that grow in birds usually can't grow in humans because the surface keys of bird viruses don't match human cell receptors. But if a new bird virus were able to infect human cells, it could overwhelm our immune systems. Where do bird flu viruses learn to infect people? Pigs. Pig cells have locks that both bird and human flu viruses can open. This makes pig cells ideal for combining genes of human and bird flu viruses. Human and bird flu genes combine at random inside the pig cell, resulting in a new type of flu virus, one that no human immune system has ever seen before. So instead of the keys gradually changing, the new virus keys have changed completely and all at once. This is antigenic shift. And such dramatic change has the potential to make everyone on the planet sick. Human viruses are highly adapted to growing in human cells. These viruses reproduce thousands of times in human cells, gaining access using specific receptors that match molecules on cell surfaces. Like athletes, they get stronger and stronger by continually training under the same conditions. And yet, it's this very strength that makes it possible to weaken the virus. This weakening is the key to making live vaccines. How do scientists make this kind of vaccine? By forcing the virus to grow in different kinds of cells in the lab. In these chick embryo cells, most of the virus particles that were so good at growing in humans can't access the chick cells. But with sheer numbers on their side, a few virus particles are able to unlock the chick cells, infect them, and begin adapting to this new environment. The virus adapts by modifying its genes, but